So let me just turn over to the other PowerPoint presentation. Okay, here we are. Okay, so let me just bring that up. Okay. So all of you should be seeing this. So today we'll talk about Ohm's law and power, and then we'll have a little demonstration afterwards on Ohm's law. So we're going to talk a little bit about voltage, current, and resistance, talk about Ohm's law, about the power law, and then the use of Ohm's law, and then a little demonstration of a little circuit and what it can measure. So we always talk about voltage and current. We may talk about power. Often it's not related to voltage or current, but rarely we talk about resistance. So we'll be covering all three of these. So, some examples, if you look at it simply, you have a power source, which could be a wall wart or a battery or a power supply that supplies a voltage. And some people look at the current or the power rating of it, but normally we're concerned about the voltage. And then we look at the load, and the load could be a light bulb, a toaster oven, cell phone, a radio, etc. And we normally try to match the voltage, and we sometimes we look at the current and power rating, but often don't, and we never really look at what the resistance of the load is. And we'll see a little example of why it sometimes can be a little bit difficult when we look at it. So when we look at a voltage, it's basically the potential difference between 2 points in a circuit. And it's similar to pressure in a mechanical water system, like a hose that you have in your garden hose, for example. And we measure voltage. We measure voltage in volts. And then when we look at like in the mechanical system, it's the flow of the water. Although we don't measure the flow in the water, usually, we would do this with a flow meter. And in electricity, it's the flow of electrons in a circuit. And this we measure in amps. And to make it work properly, we need to match voltages. So typically, we have USB voltage, with its 5 volts, and then computer monitors may go up to 15 or 19 volts in their power pack. Now, if we don't match the current or the power rating of the power supply, either the power supply gets very hot because it's drawing a lot of current, or if it can't supply enough current, it takes a long time to charge the battery, or the battery doesn't charge at all. So it's important to look at, the power and the current ratings of the various components that we have. So, but we never ask, what is the resistance of my computer or my cell phone? Um, so when we look at resistance, it's basically what prevents the flow of electricity in a circuit. And it's similar to a valve in a mechanical system. So, as you close down the valve, the flow slows down and the pressure can increase. And the same thing happens with a resistor in a circuit. And this is measured in ohms. So when we look at it simply, we have a power source and then we have a load. And, if we look here in a simple circuit, we have a battery, the current flows, it flows through the light bulb, causes the light bulb to glow, and just flows around the circuit. So this is sort of a pictorial diagram, and we'll actually look at this circuit in more detail as an example. And if we were to draw it out, we have, 25 volt source. and we have a resistor here. In this case, it's 3,500 ohms. And then if we measure the current, we'll end up with 7.1 milliamps. And we'll actually be doing some measurements. So when you look at Ohm's law, it's basically E equals I times R. So voltage equals current times resistance. So with this circuit here, you place the voltmeter across the resistor because this is what you're going to measure. And then you have a current meter here. And if you take the values that you get, if you multiply the current times the resistance, you get the voltage across the resistor here. And we'll be demonstrating this. So that's what Ohm's law is E equals I times R, or voltage equals current times resistance. So, do we actually really need to, do we ever use Ohm's law? In general, no. Uh, but if you're into electronics, you may use it sometimes. So in the advanced qualification course, we're actually going to look at using an oscilloscope and a 50 ohm dummy load and calculating the power output of a transmitter. But other reasons you may use it is if you're building a voltage divider, or using a power attenuator, or designing a resistor for an LED circuit. So let's say you have 5 volts, and you want to drop that down to 3.3 volts because it's coming out of an Arduino. Then you might use a resistor and you can calculate it. And we'll actually do some of these calculations in the future. Or if you're using a Zener diode in a power supply, you can calculate what value of resistor you can use. So we'll be looking at these later on. And then the second thing is power. So we have another formula for power. And power is the rate at which an electrical energy is transferred in a circuit. And the measure is a watt. Often we don't measure this directly. If you're doing AC power, you can get an AC power watt meter. And when we talk about RF, we'll talk about measuring RF directly. But in most cases, when we're talking about AC power or DC power, we calculate it. So if we look at power, it's developed by this formula: P equals I times E, or power equals current times voltage. And here are some of the things you can remember. So, you can draw this as PEI, and then you just put your finger over what you want to calculate. So if you want to calculate power, it's E times I. If you want to calculate E, it's power divided by I. And here, if you want to calculate I, it's power divided by E. So yes, we have the same thing for Ohm's law. So if you write V or E, and current, and I and R for resistance, again, you cover up what you want to calculate, and then you have what's left over, either multiplying or dividing. And if you look at this, if you know any of the two parameters, you can calculate the third. So here are all the various formulas that you can come up with. So we don't really use a lot of these. Like when we look at the power in an oscilloscope, we'll use this E squared divided by R. But all the rest we don't really use. And you can actually calculate what from substituting the two formulas using some algebra. But if you need to look it up, these are the different values. So basically you have your potential difference, which is your voltage, which is trying to push current through an opening or a resistance. And so ohms is how big this little gap is, and then current is whatever gets through and that you're measuring it. So why do we use power? Well, one of the things is resistors are rated in power, And if you use the wrong size of resistor, it can heat up and can burn out. We have power supplies and battery boxes are rated in volts and amps. Some of the things you have to be careful with, especially with battery boxes, is that the power that they quote may not make sense. Because if they supply 12 volts and 5 volts, they'll probably quote the higher power value in their advertisement, which gives the impression that it's supplying more power for 12 volts, but it's actually supplying that amount for 5 volts. So that's where you can go back and use your P equals I times E formula and see, put in 12 volts and what power they advertise and see how much current you get, and then put in 5 volts and 12 volts and calculate and see what the I comes out, and if and see if it makes sense with what specifications they quote. The marketing, they'll quote the higher values. And then also we have DC power requirements for radios, and this is in volts and amps. And we'll be talking more about this when we talk about batteries and DC power and power supplies. But here's an example. Quite a few. It can change quite a bit depending if you're receiving or transmitting. So let's say if we look at an ICOM IC 7300, if it's operating at 13.8 volts. And when we talk about batteries, we'll see where this 13.8 volts came from. So, if it's receiving, it might draw 1 amp of current, which is 13.8 watts. And if you're transmitting full power, they claim in the specifications it's 23 amps. So if you use the formula pi and multiply these together, you get 317 watts. So then if you want to buy a power supply, you need a power supply that is at least rated at 318 watts. And they typically sell like a 30 amp power supply, 13.8 volts, which is like 414 watts. So it's overrated, and you typically want to buy something that's overrated in the power supply, unless you're looking for something really small, or you're limited by the size. And then also, you have to look at the duty cycle of the power supply. Is it rated for 30 amps continuous, or it might only be rated 30 amps for, maybe a few minutes on and a few minutes off. So you'll have to factor all those things in. And it becomes particularly important, when you're doing solar panels and batteries and trying to hook that up and make it all work for the longest period of time. And we'll cover some of that when we look at batteries. And later on, we'll talk about RF power. How much power do you need coming out of your radio, and that's measured in watts. Typically your smaller radios are anywhere from 1 to 5 watts. Your handhelds, might be 5 or 10 watts. And then when you get into your mobile radios, you typically, you're getting into 10, 20, 30 watts, up to 50 watts. And then when you're getting into base stations, it's 100 watts sort of minimum. But when we look at this, we also have to look at propagation, feed lines, transmission lines, unknowns and balance. And there is a YouTube video that we did, 6 or 8 months ago on unknowns and balance that's up there. And then we have to look at antennas and antenna tuning. So that's all coming up in the weeks to come. And and then we talk about AC power, and AC power is more for the advanced qualification. We'll just quickly go over it, but we won't go into details on all the calculations and how it all works. That's part for series 2 on the advanced one. And then we're going to introduce a new device today. We introduced the multimeter, which can measure resistance, but we're also going to introduce this, which is known as a component tester or a transistor tester. And you can, it's got 2 leads or 3 leads, and you can hook various things to it, and it'll actually identify what you have. and also maybe tell you some of the parameters of, of a transistor or a diode. And you can also buy one of these that has a transistor tester and an oscilloscope and a signal generator right built into it, which is this one at the right hand side. So this is for low frequency work, but it has a lot of things built in if you're just interested in experimenting. Here is one that has like a nicer case to it and some test leads. And here is one that's just bare bones. We'll be using something like this, and they range in price from $5 to $50. And here, for example, they put a capacitor in here. So it says it's, between leads 1 and leads 3 is a capacitor. Here's the value of the capacitor. And then there's some other parameters of the capacitor, such as the resistance of the capacitor and also the voltage loss of the capacitor. So when we look at capacitors and inductors in series and in parallel, this is a simple way of measuring it without spending hundreds of dollars in expensive LCR a type of analyzer. We'll just use this. And the one I've got here, I think, cost me about $5 that we're going to be using. So any questions on that before we get into the actual demonstration? Okay, so let me just stop sharing this. And let me turn on the camera and we'll see how the camera works today. All right, so you should be seeing this circuit here. And what we've got here is basically a battery. So it's two batteries in series. So it's 1.5 and plus 1.5, which will give us 3 volts. This is the negative side of the battery, and this is typically the ground. So we typically try not to put any control or anything in the ground side of things, but it doesn't matter if the switch was here or if the switch was there. Then on this side, which is the positive side, we have a push button, and then we have a light. And then we also have a resistor. So we're going to try this circuit using a light, and then we're going to use a resistor. I like to use the light initially because you can actually see that it turns on, while with the resistor you can't really tell. So if we let's just take what you should be doing is disconnecting whatever you're trying to measure with your meter. So when I press the test button, it should come on. Let me see if I can just focus that a little bit better. And it says testing, and it tells me it's got a resistance of 1.68 ohms. So that roughly, let's just say 2 ohms. So between, if you take 3 volts and divide it by 2, this light bulb should take about 1.5 amps. Now we can measure the same thing using our multimeter here. And if we turn our multimeter to resistance, let's just, we will read low, which means it's open. And then when we short these two things out, it'll tell us how much resistance we have. So it'll tell us 0. So now when I put it across the load here, it's going to also give me a value. So it tells me it's about 1.1 ohm. So it depends on what instrument you buy, and there's always a tolerance to resistors. So it's not going to be as accurate. So it's going to tell me 1 ohm. So if I look at this, I'm looking at current that is over an amp, at least over an amp. So when I actually put this in, and what I'm going to do here now is switch this over to volts. So I'll turn the multimeter over to volts. So I'll turn it to a 20 volt scale, and then I'll connect this It doesn't really matter how you connect it. If you connect it the opposite way, it'll tell you that you've got the things reversed by having a minus sign on it. So voltage is connected across the resistor. So if I press this now, okay, it'll tell me I've got 2.93 volts. So that's relatively close to 3 volts. There'll be a little bit of a drop because the battery actually has a resistance, and we'll actually measure in one of the maybe next week, is calculate the resistance of a battery. So that's one thing. Now, if I want to measure the current, what I need to do is set this to current. So I'll set it to 200. I could set, let's say, 200 milliamps. And let's just see what happens. And to measure current, I have to break the circuit. So I can break the circuit either here or up here. So I'll just break the circuit down here. Put this here closest to the positive terminal. And then put this over here. So let's see what it tells us we're going to measure in terms of current. So it's telling me that it's using 163 milliamps. And the voltage has dropped a little bit because the battery is dropping on the load. But that's nowhere near the 1 amp or 1.5 amps that I was expecting. Now the reason for that is that the lamp is actually a non-linear circuit. The resistance changes, so it starts off with a high resistance and becomes a low resistance. So um, so that's one of the reasons you shouldn't use the lamp to as a dummy load on a, on a transistor amplifier or transistor transmitter, because the changing in resistance puts a lot of strain on the transistor, and you can actually end up burning out your radio if you use the lamp. So sometimes your resistance values are off because you're using something that's nonlinear like the lamp. Now let's just take this and use a resistor. So if I take this and so this is a 100 ohm resistor. So it's got a color code on it. So the color code is black, black, brown, and then it's got a gold stripe, which means a 5% tolerance. So it could be anywhere from 95 to 105 ohms. And then if I switch this back to resistance, it's telling me it's 98.7 ohms, so which is good. So let me turn this one back to voltage, and let's just measure it with our other one. So this one is telling me it's 99.4 ohms, so still within the plus or minus 5% value, so that's good. So let's see when we have a known resistor and we put a known resistor into the circuit. So what I'll do is I'll put this in. I'll put on the meter again for voltage. So now when I press the button, it's telling me 2.9 volts, 29 milliamps. So if I take 2.9 volts divided by 100, gives me 0.297, which is 0.0297, which is 29.7 milliamps. So here Ohm's law works and everything happens to work as it should, but you can't really tell, with the resistor, because, I mean, you might be able to feel a little bit of heat. This is probably looks either a quarter watt or a half watt resistor. So if we calculated the power, it's probably maybe about zero point 0.1 watt. So I mean, it's well within the characteristics of the resistor. So this tells us what that Ohm's law is working, and we get the right value. Next week or the week after, we'll look at what happens if we put two or three resistors in parallel and two or three resistors in series, and we'll be measuring voltage and power of those. So let me just stop sharing this and turning off the recording.